you can do the integral here. Take E, be good, great job. The graph of force and time. So we have the impulse, which is the area under the curve, impulse. The change in the card momentum, the change in the momentum is equal to the impulse, which is the area of under this graph, and you estimated that like doing graphing a triangle, so that the area of the triangle approximately equal to the area of the under that graph, like that triangle, Question 8 and 10. Okay, 8, 9, 10, difficult. Identical satellites X and Y of mass small m are in circular orbits around the planet of the mass big M. The radius of the planet is r. The satellite X has an orbital radius 3r and the satellite Y of the radius 4r. The kinetic energy of satellite X is kx. In terms of kx, the gravitational potential energy of the planet satellite system. You just need to use the formula for gravitational potential energy. Let me find that in the beginning of the test. The formula, as I remember, potential energy EPU, or just use the letter U. Potential energy is minus of G, the mass of the center planet, which is the big M here, the planet, and then divide the distance between the satellite and the center of the planet, which is 3r. So this is the formula for the potential energy, gravitational potential energy of the satellite. Okay, and we need to represent this kx in terms of these things also, mass m and 3r, so that we can find the relationship between the potential energy and the kinetic energy is 1/2 mv squared. So now we need to represent the v squared in terms of big M, small m, and radius. This is a centrifugal motion, circular motion. So we have a formula, centrifugal force, which is gravitational force. Gravitational force is G big M small m over r squared, remember? It is equal to the centrifugal force, which is the mass of satellite, times the square of the velocity over the radius. V squared over r is the centrifugal acceleration. From this formula, we can get the V squared, okay? So we can represent the kinetic energy in terms of big M, capital G, and R. Simplify them, simplify M here and R here with the square. So square of V is Gm over R, and the kinetic energy is 1/2 of this thing, big G, big M, small m, and R. So now the next thing, you just need to compare these two things. Compare the kinetic energy and the potential energy, so you can find the relationship between them. Oh, sorry, I made a mistake here. Because the distance from the satellite to the planet is 3r, not r here. 3, this one is also 3r, and 3r squared is 9r squared. Okay, need to fix this one. Because the radius is 3r, the distance from the satellite to the center of the planet. So the 3r squared is 9r squared. Okay, so after simplifying, the speed is Gm over 3r. And this kinetic energy is like a half of the potential energy and opposite in the sign, right?
Yes.
Half of the potential, but opposite in the sign. It's like the potential is like -2 and the kinetic energy is 1. So the relationship is the potential energy equal to 2 times of the kinetic energy and negative, meaning answer A. Now question 11, about 10, where's 10? Up here. Satellite X is moved to the same orbit as the satellite Y. X is moved further, by force doing work on the satellite. In terms of K, the work done on satellite X by the force is the work done on the satellite. So that work has two effects. That work must increase the potential, change the potential, and change the kinetic energy, both things, changing both potential and kinetic energy of the satellite. Okay, and we have the formula of the potential energy U is minus G, and the mass of the satellite, the mass of the planet over the distance. The initial potential A over 3r, and the final potential when moving, let's write this is ux, ux, and then when we move it to the new orbit Y, the new potential energy is big M, the two masses product, and then 4r. Okay, so it's like more negative potential. But the point is the planet attracts the satellite, gravitational attraction, and therefore to push it forward away from the planet, we must do a work. Okay, must do work, must provide the energy, burning the fuel to push the satellite away. So when we compare the potential energy, taking uy and minus ux, like 1,3 minus compared to 1,4 minus, which one is greater? 1,3 is point like 3,3, and this is 0.25. So this one is greater, huh? Meaning the potential energy at the orbit Y is greater. So this one is greater. So we have provide the energy for the satellite to increase the potential energy of the satellite, and also we have to increase the kinetic energy as well. So that work is equal to the change in both kinetic and potential energy, which is mechanical energy, ky minus kx, and then plus uy minus ux. Okay, this is the answer. So now we need to find the relationship between ky and kx. Kx over ky is 4 over 3. 4 over 3. So ky is 3 over 4 kx. Huh? Wait, so that is less kinetic energy, because according to this formula, the v square is gm over the square, the radius. So the further the radius, the smaller, the lower the speed. Huh? Yeah. So that's less kinetic energy. So ky there is 3/4 of kx minus kx, and then the difference between the potential energy is this one. And we also can represent those things. Ux is minus 2 times of kx, huh? Minus 2 times of kx, and you need to also represent uy. Wow, complicated problem, huh? Ux is minus 2 times of kx, and in front of that, of course, ux is a negative value, or we can find that difference and then represent it in terms of kx. So uy minus ux is minus gm over r, 1/4 minus 1/3, huh? Okay, 1/4 yes. Minus 1/3. Doing the subtraction. Wait. Yeah, bring the negative side to the front. So this thing is 3 minus 1, or 3 minus 4, which is minus 1 over 12. Then time minus gm over r in the front. So that is gm over 12r. And how does that relate? We need to also multiply with the small m. So how does that relate to kx is this one? Kx is 1/6 of gmm over r. So this difference between the two potential energies is half of the kx, huh? Okay, plus half of kx. So this is the final answer. 3/4 minus 1 is minus 1/4, minus 1/4 plus 1/2. That's 1/4, huh? 1/4, meaning this one. Check that with the answer 1110.